Okay, so let us start. Welcome to all and very warm good morning. We already discussed some important features of the topic of physical vapor deposition. Means how physical vapor deposition systems was work and what are the two or three most important processes. We also look it in short. Now today we will plan to focus on the thermal evaporation system which already incorporated in the type of what physical vapor deposition. So today we will try to focus and try to finish the topic of thermal evaporation system. Okay, so if we look into the thermal evaporation system, so we have already covered the basic of evaporation, means how the metal
बस
was formed. So we already discussed some uh, method about the evaporation, how and how and why thermal evaporation system was work. Okay, and what is the role of thermal evaporation system. Okay, that point little bit point we already covered in our last lecture, that is yesterday's lecture. So today we'll focus on thermal evaporation system and ion sputtering. Okay, so look at here inside the slide, so we can see the for evaporation, the background pressure in the vacuum chamber is typically 10 raised to minus 6 torr. Okay, so whenever we want to melt a particular material inside the chamber, and that metallic ion or that metallic atom or that metallic material we want to deposit onto the substrate in the form of thin film. So inside the chamber we need a 10 raised to minus 6 torr vacuum. It means if we think about the in terms of Pascal, so it needs a 10 raised to minus 4 Pascal or lower than that. Okay, or lower than that. It means it may be around 10 raised to minus 7 torr, it may be around 10 raised to minus 8 torr, or it may be at around 10 raised to minus 9 torr. But above the 10 raised to minus 6, it means 10 raised to minus 5, 10 raised to minus 4, 10 raised to minus 3 torr. So if that much amount of vacuum is available inside that chamber, so the important point is that we cannot run the system, we cannot start the thermal evaporation system, that is mean by physical vapor deposition system. Okay, so first important key point of thermal evaporation system is that there is required a 10 raised to minus 6 torr vacuum. Okay, and if we look in the other section that the sputtering purposes, it is required a background pressure in the vacuum chamber is typically around 10 raised to minus 3 to 10 raised to minus 2 torr. Okay, it means that much amount of vacuum is enough to start the system. Which system? Ion sputtering, not a thermal evaporation. Okay, so it might be asked for the last examination or maybe a internal examination, the difference between this point, or maybe in a multiple choice question purposes. Okay, so if we need to start this system of thermal evaporation, so we need a vacuum around 10 raised to minus 6 torr, and that pressure or that vacuum we can create by using the turbo pump or diffusion pump. Okay, so in this case we need a diffusion pump, otherwise I will write here for the better purposes, we need a diffusion pump or turbo pump. Okay, and and for the case of sputtering purposes we need a only rotary pump, and the rotary pump is enough to create a vacuum around 10 raised to minus 3 torr. Getting my point? So you have to remember this part, okay, which we have already discussed in the module number first. Okay, so let us discuss about the thermal evaporation system in detail. So what will happen in thermal evaporation system? In order to evaporate a material, it must be heated to temperature at which its vapor pressure is 10 raised to minus 3 torr or greater than that. It means here the word mentioned 10 raised to minus 3 torr, but you have to consider the value is around 10 raised to minus 6 torr. Okay, you have to consider the value 10 raised to minus 6 torr. Okay, or we can say that greater than 10 raised to minus 5 torr, less than 10 raised to minus 5 torr. But for the better and good quality of response during the thermal evaporation purposes, so it must be a vacuum is around 10 raised to minus 6 torr. Okay, and that time we can melt a material. Okay, so for example, aluminum must be heated at 1000 degrees Celsius or more. Okay, so inside the thermal evaporation system, if we want to deposit a aluminum material onto that particular substrate, so at that time inside that chamber we need a 1000 degrees Celsius temperature. Okay, and at that time that aluminum material gets evaporated, okay, in the form of vapors, and after some condensation process that aluminum particles can be deposited onto the substrate. Okay, so that due to remove the unwanted air, unwanted other molecules, and easily that aluminum particle can accelerate towards the substrate side. So due to that reason we need a vacuum. Okay, so there are two common ways to heat the source material. Okay, which source material? Now we are taking the example of aluminum. Okay, and if we want to heat that particular source, and that is nothing but a aluminum, so there are two basic categories, or okay, or common ways, that is resistive heating or electron beam heating. Okay, one is the resistive heating and another one is the electron beam heating. So what is the work of resistive heating and how we can apply that resistive heating onto the heating purposes? Okay, so resistive heating are used electric current flow through a tungsten filament to heat the source material. Okay, it means of course there are tungsten filament was placed inside the chamber, and that tungsten filament was connected to the current and voltage uh, section, and whenever that we will pass the current and voltage, it means particular amount of current and voltage. At that time the tungsten filament was heated, and simultaneously that source was also heated. Okay, or if that tungsten filament temperature gets increases, simultaneously the source temperature was also increases. So it means the source material can be placed directly on the tungsten filament. Okay, suppose this is the tungsten filament. If let us consider that the tungsten filament, and here is the some part of crucible. Okay, and that crucible, inside that crucible the source of that particular aluminum material was placed inside that crucible. It means, if suppose that blue portion indicates our aluminum source, and the red portion, this portion indicates a W, that is nothing but a tungsten filament, and here that portion was connected to the I and V current and voltage section. Okay, here. Okay, so that the source material can be placed directly on the tungsten filament, or it can be put in a crucible that is heated by the filament. Okay, so I have drawn some rough picture here for your better understanding purposes. Okay, so that is much nothing but a resistive heating method. Okay, so I hope that you might be clear this slide. Now we will move towards the electron beam evaporation system side. Okay, now let us discuss about the electron beam heating. Okay, which is not incorporated inside this slide, but what will happen exactly in electron beam heating? So electron beam is nothing but a e-beam evaporation system, a highly intensity beam of electrons having the energy is up to 50 kilo electron volts is focused onto the source material. Okay, it means we can say that by taking the example, if suppose this is your material, this is your material, and electron beam was applied or focused onto that substrate. Okay, here, and what will happen, the energy of that electron beam is approximately or up to 50 keV, 50 keV, and that means 50 kilo electron volt. An electron bombardment hits the source material. Okay, so whenever that electron was bombarded onto that substrate or not a substrate, that particular source, and at that time the source material to be temperature required for evaporation. Okay, and that time heating can be restricted to the source material itself, and the surrounding stay is cool. So inside that chamber whenever we apply the electron which is bombarded onto the source, at that time that material was heated and simultaneously that particle was evaporated in this way. Okay, so because if inside this chamber the pressure is so low in the vacuum chamber, in evaporation the source material travels in a straight line. Okay, so is very interesting phenomena is here. So inside this particular chamber, that chamber, if the pressure is very low, it means inside there is a negligible amount of or no any other particles are present inside that chamber. So the main or important part was going there is that in evaporation of that particular source materials travels in a straight line. Okay, and here if the substrate was located, here if the substrate was located, the evaporated material goes in a straight line, goes in a straight direction and directly deposited onto that particular substrate in the form of thin film. Okay, so this is about the electron beam evaporation. Now we will focus on the topic of, or we can say that we will try to cover the electronic or experimental procedure of thermal evaporation system. So how the system was work, we will try to cover by taking some pictorial images. Okay, so look it into that figure. Look it into that figure. So what will happen inside that figure? So here is your source material. Here is the your source material which is connected to the heater. Okay, here the heater evaporator, or we can say that heated evaporant was putted, or it means the tungsten filament was inserted inside that chamber. Okay, and that filament was connected to the voltage and current which I have already discussed in our last slide. Okay, here is the vacuum pump was connected, here is the vacuum pump was connected. Okay, and these are the shielded region, these are the completely shielded region, this portion was completely shielded. Okay, so that if that sheltered region was completely sheltered by some of the high quality of glasses, or so at that time what will happen, if the 10 raised to minus 6 torr vacuum is available inside that chamber, so what will happen, that source material which I have written here, source, and this is the your substrate, Okay, here we can write down by using the this way. This is your substrate. Okay, so if the source material was heated and that particle was evaporated, so that particle was completely deposited onto that substrate. Okay, and here these are the evaporated atoms. Okay, so for the better understanding purposes, I have again show the this particular shaded region in the form of in this way. Okay, in the form of in this way. So again you have to look or imagine that this is your crucible where we are mounted or where we are placed our source material, and this wire was this wire indicates a tungsten filament. Okay, that wounded part is indicates that particular wounded part. Okay, it means this wounded part is nothing but a tungsten filament, and after that that wire connected to the electronic apparatus. Okay, and if we apply the particular or some amount of current and voltage at that time, that filament was heated and that aluminum vapor was formed. Okay, aluminum particle was evaporated, and that shaded portion, that triangular type of shaded portion indicates a aluminum vapor. Okay, and after the evaporation of that particular aluminum atoms, okay, that particular atoms aluminum atoms was completely deposited onto the silicon vapor. Okay, so here the substrate are used in the form of silicon vapor. So substrate is nothing but a silicon vapors are used substrate. So in this case, for the example purposes, substrate. So here the silicon vapors are used. Okay. So substrate is nothing but a that silicon vapors are used. So I have write here silicon vapor. Silicon vapor are used. Okay, fine. So now that particular shaded region, which shaded region? That green part of that shaded region, this particular portion, that shaded region is nothing but a aluminum film. Okay, and that aluminum film in the form of, we can say that in the range of some micrometer to few nanometers. Okay, it may be depends upon our, it may be it depends upon our application, or it may be depends upon our interest. Okay, how much thin layer we need for the further technique purposes. So by that requirement, we can evaporate a particular aluminum vapors or aluminum particles, and that particles we can deposit onto a silicon substrate. Okay, so one important point I would like to say that, or I would like to share that the substrate are different yeah, equipment, or we can say that substrate uh, we can use as per our choice, as per our requirement. Okay, so sometimes some of the fellows are used as a silicon uh, vapor, or as a quartz vapor, or as a glass particle, or glass substrate, or some kind of, sometimes they are used as a copper substrate, as a zirconia substrate, as a titanium plate. Okay, so as per the application, as per the choice, as per their requirement, they are used different types of substrate. Okay, because as per the requirement, which layer or which good quality of thin film layer we can deposit on that substrate, so that type of substrate we can use. Okay, so here the silicon vapor are used as a substrate because on the silicon substrate the aluminum film was grown in very purely or very fantastically. Okay, and maybe that purposes the silicon vapors are used here. Now here I will show you So how the I will show you one video, or that is the one animated video for the better understanding purposes. So I request to all to look that this video carefully. So how the thermal evaporation was formed exactly for that animation, or from that animation you might be clear the total concept of thermal evaporation. It means how the atom was evaporated and how that particular atom was deposited onto that substrate. Okay, so look at here. I again start the video. Now the metal particle was heated and completely that particle was evaporated, and after some time the metal film was formed. That is the thin film of that particular metal was formed. Okay, and below is the heating coil or heating plate. Okay, so this is all about the thermal evaporation system. So now we will try to focus on some mathematical relation of physical vapor deposition system, so that the physical vapor deposition system there is some mean free path, okay, from where the particles can travel from the source to substrate, and that atoms or molecule in the chamber at pressure P. So that mean free path is nothing but a lambda. Lambda is equal to kt. K is here Boltzmann constant, T is the temperature, means whatever amount of temperature were applied. So small k capital T upon root 2 pi capital P d square. So T is the absolute temperature, whatever amount of temperature were apply here. So T is the absolute temperature, K is the Boltzmann constant, and that K value is always constant, that fundamental constant value of Boltzmann. Okay, and this is the diameter of the gas atom. Okay, so the gas atom means whatever amount of that it may be a argon gas atom. Okay, so this mean free path is a this concept is applicable in the type of ion sputtering. Okay, so that's why the D is the diameter of argon gas atom, or we can say that the argon gas molecule. So that the mean free path is the average distance between the collision in the chamber. Okay, so the mean free path is the average distance between the collision in the chamber, means that atom or a substrate to the source. Okay, source and substrate, that distance or that average distance inside that particular chamber. So this is about the uh, this formula, or that is the mean free path formula. Okay, so physical vapor deposition purposes, if we took some value at room temperature and for a typical atom per molecule diameter of 4 angstrom, the previous, as per the previous equation, so we will get a lambda is equal to 5.8 into 10 raised to minus 3 upon capital P in a meter value. Okay, so the pressure is in a Pascal here. Okay, so here the pressure are used in terms of Pascal. So 1 Pascal is, we know already that term, 1 Pascal is equal to what? 1 Newton per meter square, and that is 7.5 into 10 raised to minus 3 torque. So what is mean free path for the typical evaporation and sputtering condition? So that mean free path we can calculate if we know the value of the temperature or pressure. That is the pressure. Okay, so if we know the P, or P means how much amount of pressure we applied here, but this value, okay, but this value is only for a room temperature. That is, we generally count a 27 degrees Celsius. That is our room temperature value for a typical atom per molecule diameter of 4 angstrom. If that atom and diameter value is approximately 5 angstrom, and in that case, this relation we got the value of 5.8 into 10 raised to minus 3 upon capital P. and if we know the pressure or vacuum of that particular atom, whatever we are evaporated onto that chamber, so that time we can calculate a exact mean free path from source to the target. Okay, so this is all about the what, all about the thermal evaporation. Now let us focus on the ion sputtering. Let us focus on the ion sputtering. So the in sputtering purposes, here look at here the type. In sputtering purposes, the source of material is usually in the form of sheet or plate. Okay, so below this portion is our substrate. Yellow portion indicates a substrate, and green portion, this portion indicates a what, thin film of our target material, not a target material, that is our source material. So source material means whatever amount of atom was deposited, that is our thin film, which we finally obtain. Okay, so below is our below is the substrate, or we can say that this, that may be a silicon vapor, that may be a aluminum vapor, that may be a polymer vapor. Okay, and whatever amount of that sputter target atom was deposited onto the thin film. Now the above part, okay, now that particular above part, that is the sputtering target. Okay, and the source material is usually in the form of sheet or plate. Okay, that is the target material. Okay, so here the ion sputtering purposes, it, if we need to deposit some kind of atom, so at that time that particular material or metal or targeting material, that material is required in the form of sheet or maybe a plate. Okay, so second thing, that but all the entire chamber was also placed inside the vacuum, or after that sputtering is achieved by the bombarding the target with energetic ions, and that energetic ions generally used as a argon plus ions. Okay, and from where, somewhere the argon gas was placed. Okay, this is the argon gas cylinder. Okay, and here some cork is also available here, and from where the argon gas is passed inside that chamber. Okay, and now there completely the argon ions was ejected inside that chamber. After that, that argon ions was goes toward the sputtering targeted. Okay, so sputtering is achieved by bombarding the target with energetic ions, and that energetic ions, these are the energetic ions, these are the energetic ions, and that energetic ions is available in the form of argon plus. And after that the atoms on the surface, okay, atoms on the surface of the target are dislodged by this bombardment and fly off. And after that, whenever that argon ions was bombarded, okay, that argon ions was bombarded onto that sputtering target. After that, what will happen when, if suppose these are the aluminum plate is there, so after that the atom of the surface of the target are dislodged by this bombardment and fly off. That aluminum particle, that aluminum atoms are dislodged, and after that that aluminum particle was separate and separated, and after the few moment that aluminum particle was comes and struck and deposited onto the substrate. Okay, so after that these atoms then impinge on the substrate and resulting in deposition of the thin film. Okay, so what will happen exactly, in short, that argon atoms or argon gas, whenever we pass the inside that chamber, that argon gas or argon atoms or molecules or ion was struck onto the targeted material or bombarded onto the target material. That arrow indicates, that black arrow indicates that the argon ions was bombarded onto the targeted material, and after that the diffusion was formed inside the target material, and due to that reason, the not a diffusion, we can say that there are some reaction was formed, and that target, from that target material, aluminum particle or aluminum ion was separated, and that aluminum particle was free from that sputtering targeted, and after some time that aluminum particle was deposited onto the thin film. Okay, and after few moments that argon gas ions was ejected from this chamber in this way. Okay, so argon gas is passed from this chamber in this way, and after that bombardment of argon ion onto this sputtering target, when that aluminum particle was free, and after few moments that argon gas was ejected from that particular chamber. Okay, so that red circle, inside that red circle, that is, these are the aluminum particles or aluminum ions. Okay, and which is deposited onto this particular area, and that area is nothing but a thin film area. Okay, and the substrate, I already spoke, that substrate is nothing but a, it might be a silicon vapor, it might be a metallic any other vapors, or it might be a uh, vapor, I'm calling a vapor, not a vapors. Okay, or it might be a glass plate, okay, or glass slide. Okay, that is a substrate, and which are connected to the grounded. Okay, so this is all about the sputtering process. Okay, so I hope you might be enjoyed the lecture of today's portion or today's point. Now I will show one video. Look at here the ion sputtering purposes. So what will happen exactly? This is the plate, or this is the targeted material. After that, the rubber vacuum gasket, from where if we use the rubber gasket, so very negligible chances from where the vacuum was leaked. Now ion sputtering was started. Now vacuum is completely increasing. Look at here carefully. What will happen exactly during the ion sputtering time? Now gas is passed. Glass now being covered or sputtered. After the few minutes, the thin film is deposited. Copper can be seen easily. So now the copper was deposited onto that film. Look at here. This is the copper thin film. Okay, so copper metal was deposited onto the glass slide. Glass is the substrate. Okay, so that type of process was happening